I got friends in New York City, 'cause everyone I know left town.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard. Welcome everyone. In this video I will be talking about the units in physics calculations, about the things that should be taken into account. First of all, the most important things about units in physics is that you have to carry them with you when you're performing calculations. Not is it only wrong to leave them out, but having the units serves as a nice check that your calculation makes sense to a certain degree and that you are carrying all the right quantities with you. So as an example, let's calculate the average velocity of a vehicle, for example. So we start with this formula, S equals T times V, and we want to evaluate what is the average velocity. So of course we solve for V. That gives us the distance covered divided by the time that it takes to drive that distance. This is a car driving on the road. So let's say the distance is 200 meters and that is covered in 10 seconds. Oh, my bad. Of course 200 meters only, not meters per second, and the time is 10 seconds. So this gives us 20 meters per second. So whenever we are evaluating this kind of expressions, we not only deal with the numbers, but we have to be equally consistent with the units. So in this case we have meters divided by seconds, so we must have m over s in the answer as well. In a lot of times you have to convert between the units as well. So for example, how much would 20 meters per second be in miles per hour? Or another typical one is how much is this in kilometers per hour, for example. Well, let's do the example of miles per hour. So instead of, for generality, instead of having this 20 meters per second, let's see how much is 1 meter per second in miles per hour. So how do we start? So the problem is that we have meters here when we want to have miles, and seconds instead of hours. So first of all, we know that 1 mile is 1,609 meters. So let's solve for this 1 meter here. So we get, in fact, 1 meter is 1 mile divided by 1,000. So that's a meter there and a mile there. So we are carrying the units as we are supposed to. And then the same thing for, what about the second? So we know that 3,600 seconds equals 1 hour. So how much is 1 second? So 1 second is 1 hour divided by 3,600. And now we plug these guys in to what we have here. So we have 1 times, how much is 1 meter here? 1 meter is 1 mile divided by 1,000, and that is divided by the second, which by definition is 1 hour divided by 3,600. So what do we get from here if we multiply the numbers and also evaluate the expression of these units? So first of all, we have 3,600 divided by 1,609. All those ones go away. and then we have, in terms of units, we have miles per hour, and the value of 3600 divided by 1609 is 2.237 miles per hour. So this is pretty useful conversation or conversion for future reference. And if you want to go the other way around, we can just divide 2.2 to the other side, and we get 1 mile per hour is same as 0.447 meters per second. And another very useful, of course, is that 1 meter per second, in fact, is 3.6 kilometers per hour, and the other way around, 1 kilometer per hour is 0.278 meters per second. We can do these unit conversations in the way that I showed to whatever units you will encounter, but these are the most usual ones that you will need, especially when we are calculating mechanical motion and the velocities involved. Now let's use one of these formulas to evaluate how much is 20 meters per second. So continuing from here, 20 meters per second is 20 times 1 meter per second is 2.237 miles per hour, and we get 44.74 miles per hour, so about 45 miles per hour. And this brings us to a quite important topic as well. So how many numbers we should represent or present in the final answer? And the answer is as many as there are significant figures in the less accurate number. So what this means is that we are multiplying 20 by 2.237. So here we have 4 significant figures. And here we have 2 significant figures. So in the answer, we cannot have more significant figures than in the term that has the least amount. So the minimum amount of significant figures of these terms, of these 2 terms, is 2. So we can only carry 2 significant figures in the final answer. So, which brings us to the 45 miles per hour. And the reason is because, for example, when we have 2 significant figures here, this means that the first one is correct, but there's some kind of uncertainty related in the last one. So there's uncertainty in the 0. So we can claim that we would have correct figures after a decimal point, for example. So we can't say it's going to be 44.7. We have to backtrack all the way to the least significant figure that we had in the calculation to begin with. So the correct answer in this case would be 45 miles per hour. That was a little sidestep, although an important one, from the units. So let's continue with the units themselves. In mechanics, there are a couple of units that pop up all the time, and conversions that are relating them to each other. So first of all, let's start from Newton. So Newton is a unit of force, and but that is, the Newton itself is not a standard unit like kilogram or meter or second are. So the Newton can be expressed in terms of these standard units. So a Newton, for example, is kilograms times meter divided by second squared. And this, of course, comes from the fact that the force is mass times acceleration. Units of mass are kgs, and units of acceleration are meters per second squared. Another one is the unit of energy, a joule, which is in fact Newton meters. And this follows, for example, from the definition of work. So if we are applying a force to objects over, and it moves a distance s at the same time, we get energy. So units of force are newtons and units of distance are meters, so we get Newton meters. What else? Pascal, the unit of pressure, as you well know, and that is, of course, newtons over meter squared, because pressure is defined as force over area. But we can, of course, express all these units in different ways. So as an example, let's continue from here. Let's multiply the units of pascals or by 1 meter, and then divide it also by 1 meter. So what we are doing here is we have newtons per meter squared. So we multiply by meter and dividing by meter, so we are not violating anything. So and what then follows is we get Newton meters per meter squared. And now we suddenly see that, oh, we have Newton meters here. That's joules, the units of energy. So basically, what we are claiming here, that 1 Pascal is some amount of energy in a certain volume. And that is, in fact, just another definition of pressure. So, for example, when we have a box full of air, the pressure within the box, as we know nowadays, is caused by the small air molecules bouncing against the walls. So the more energetic those particles are, the more pressure they produce on the walls. So this units of energy is a manifestation of the kinetic energy of the air particles in this case. So a lot of times units are not just an unnecessary evil that have to be carried around. They even might give some physical insight to the situation itself, like here.